Okay, all right, let's get started. So this week, basically last class, we finished talking about the probability and randomness. So we'll go into a little bit more about the physical design of the turbine. Okay. So before that, announcement. So it's outside the class, but it's related to power energy. So all of you should have gotten an email from me about the scholarships, right, in power and energy. So please do apply for that, right? So I know the last quarter we didn't have it, but this quarter we're restarting the scholarship program. And there's not a lot of work, just writing your GPA, writing a few paragraphs about what your career plan is, why why do you want to stay in the power space? How do you plan to contribute to society through this, and so on? And we'll take a look at the application. So it's multiple scholarships, right? So every year we have a number of scholarships. Most of them are open to both domestic and international students. And often we don't get that many applicants, right? So the chance of getting a fellowship may not be very low. So please, do consider apply to those fellowships. Any question about that? The question about the fellowships? So if you have gotten it in the past, you can still apply. Yeah, so getting it before does not prevent you from getting it again. We don't really take that into consideration. Okay, so
I might have come in a couple of minutes late. Where's the link to apply to these scholarships?
I sent out an email maybe a week ago or a few days ago.
All right, I'll look through my inbox.
Yeah, to everybody, to the UW undergrad mailing list. I know folks has gotten it because I see 2 or 3 applications already. So it's out there. But we have more than 2 or 3 scholarships, right? So I encourage rest of the folks who hasn't applied to apply. Right. So and this sort of decision, this is somewhat independent from the other scholarships in the department and in the college. So again, you having some other sort of financial support does not necessarily prevent you from getting this one. Okay. So if you don't find the link, email me again. You can email me. I'll send out the link again. But please do consider applying. These are for this quarter. So the application closes in the middle of February, and you get the money before the end of the quarter. So the fellowship will close, we'll make a decision, and then the department will process a payment, and you should get it sometime in March. You should get the money sometime in March. Okay, so the amount is about $2,000 per scholarship. Any other questions about this? Okay, good. So that's one thing. So do remember applying to apply for that, right? So the question is, if this is your last quarter, can you still apply? Yes, right. So as long as you're a current undergrad student, I guess. Right? A graduate student, you don't qualify, right? So the scholarship is specifically for undergrad student who has a good current standing. That means if this is your last quarter, you can still apply. So other questions? Okay, good. All right, so continue with the class, right? So this class will go into types of wind energy systems. Basically, we'll move towards machines. So we're getting into the machines portion, the machines component of the class. Okay. So as a reminder, right, what we have done. What we have done is we have looked at wind speed to wind power. Right? We have looked at the probability. Right? But these are mostly on the. So when we look at this sort of topics, we're basically treating the turbine as a box. Okay, so the way we look at these things as turbine is some box. And for this box, we have wind coming in, we have power, electric power coming out, right? So we've been sort of looking around this box. So the coefficient performance is sort of an abstraction of this box, basically. Okay, so we've been looking at this for abstraction. And from now, the goal is to look inside the box, right? So understand how do you make a turbine, how do you make a machine, and what goes on into making this machine. I'll look at a little bit sort of history of what wind turbines from the beginning until now, what they look like. So, right, so you look at the historical development, right? So the first turbine was somewhere early, right? Not 1888, right? So this is actually before widespread electrification, so way before that. And so I believe these are the pictures of the actual turbines. So it was in the US, Cleveland, Ohio, and produces 12 kilowatt of power. Although at that time, 12 kilowatt is not a small amount of power. Okay, so this turbine was able to produce 12 kilowatt, and the operating principle is quite simple. Okay. Basically, you have a magnet, you turn the magnet, and you produce power. So you have similar ones in Europe, right? So there's ones in Europe that produce power, okay? But these are relatively small machines. Right, so the reason wind turbines was popular was actually before the electric grid was built in the US. They were used quite often to power rural areas. Okay? They're actually spread all over the place. For small rural towns that's not connected to the main grid, you have turbines providing power all the time. So, of course, these are not reliable. Sometimes they're on, sometimes they're off, but still act like power plants, basically. Then as the grid gotten bigger and bigger, of course, at that time, having a coal-fired power plant was much, much more reliable than say having a wind turbine. So, you start seeing less and less turbines around. And then sort of the first real shock in the system was the 1970s, right? The oil crisis. That spurred a lot of more modern innovation in turbine design. Then around the late 1990s and 2000s, really you're seeing sort of this round of turbine design. Okay, so this wind, is actually not all that new if you're looking at using wind to generate electricity. Well, it's used a lot, in the 30s and 40s, for reasons that you're not tied to a big grid. So a lot of reason nowadays to use wind, actually we're seeing this trend again. If you look at microgrid, it's all again to use wind to do sort of local power, right? But of course, the electric machines has changed dramatically, right, since the 30s, right? So the inside the turbines, there's a lot more new components, right? But wind has been around, or has been a part of the grid for actually 100 years or so. So of course, this is the common type of turbine we see today, right? So we have all seen this, a blade, we have a gearbox, and we have a generator inside the housing, and then this is a big tower you see on the ground. You see these sort of towers. All right, so you see this quite often out there. And if you take a closer look If you take a closer look, inside the housing part of the turbine, you look at a closer look at the structure. This is what the turbine looks like. Basically, you have blades, right? So if you think this is where your blades would be attached, you have a hub, you have a shaft, a gearbox, then connect to a generator. Right? So this is a big mechanical machine, right? Big mechanical machine. Right? So if you look at this picture, which part of the system do you think causes most of the problems? Or is the most expensive? Take a look, sorry. So if you're building a turbine, what do you think, which component do you think go wrong when you have turbines like this? For people who have done some machines. So we have a machine like this. Right, so if you look at a turbine, if you look at this sort of structure, housing structure, it's big, it's heavy. A lot of things, if you do maintenance, this is the part you're doing maintenance on, right? So a lot of cost comes from what's inside the structure. So which component causes most of the problems? For folks who have some experience with this sort of mechanical engineering components. Main brakes, right? So the most thing is gearbox. So gearbox is correct. This is the part that causes issues a lot of time. The reason the gearbox is quite complex gearbox, right? Because wind blows at whatever speed it wants to blow at. So the rotational speed of the turbine is not all that, sometimes cannot be made constant. Okay? Then you have a gearbox. This gearbox basically, but it's tied to a generator. So if you think if this is directly tied to the grid, then this gearbox, the generator is 60 hertz. Okay? So you have a gearbox that has to do a lot of conversion, and sometimes just a big, expensive gearbox that tend to go wrong. And as we go through the class, we'll see, how we replace this gearbox. Okay, so we'll cover basically 4 types of turbines. And you can think of the 4 types as, by type 4, the idea is let's get rid of this gearbox. Okay, gearbox are the things that causes problems. Okay. So some turbines, right? So that's one thing to keep in mind is gearbox. When people say these things require a lot of maintenance, a lot of times this maintenance just happens in this gearbox. Right. Any questions about this? Okay, so this is the structure, right? So if you look at this kind of turbine, it's good to think about why we build this kind of so-called horizontal axis wind turbines, right? For obvious reasons. The axis of rotation is parallel to the ground. Right? So why do we build this kind of horizontal wind turbines? Well, if you look at the horizontal wind turbines, basically, the real advantage is this can be made very tall. This is just a tall tower. Okay? As we said earlier in the previously in the class, the faster the speed, the power scales with a cubic relationship, right? So you want a really high speed. So that's why you build a very tall turbine. You build a very tall tower. And this is high efficiency. Okay, so because the high efficiency, because this kind of rotation is, so the blade spin fairly regularly. So it's been, let's say, okay, so if you point this thing, right, towards wind, actually the 3 blades will be fairly continuous. The power it gets will be fairly uniform and continuous. So that makes things easy. Right? That makes things easy. Right. So and this this also leads to, because once you face wood, the 3 blades spins fairly continuously, and this makes this sort of have low small disturbances. Because the blade rotation is fairly, the speed of rotation, at least on a short time scale, it's fairly smooth, right? So you don't have things like transients, big voltage changes, things like that. So the main thing is just you can build very tall, but then once you build very tall, is if you can basically point, right? You can point at the wind direction, and that gives fairly smooth spin rates. It spins very smoothly. So what are some of the disadvantages of this kind of horizontal axis turbines? What are some sort of the obvious disadvantages? Why might this be hard to build?
It's going to be top heavy. So it has to be the structure might be hard to build.
Right, so maybe very top heavy. Oops, I think I signed out. Let me sign in again. Can folks see my slides again? Is it bad? Okay,
Yep.
All right, thanks. Right. So that's the one thing that has just massive tower, right? So this requires a massive tower to work, right? So if you have a tower that's 100 meters tall, it's just a big, huge tower. So it's not easy to make this work. And maintenance is really difficult. Because you need to get somebody up there to do maintenance, right? For example, the gearbox has problems. You need to do maintenance on the gearbox, and somehow you have to get onto this 100-meter tall tower, right? Which is a difficult thing to do, right? And
do they airlift the parts? Like if you have to replace a large part at the top, how do you get it up there?
You can't airlift it; it's too heavy. So you basically, it's like how you build a tall building, right? So you have a crane and that's lifted up. So think of building a 100-meter tall building.
Okay, so when they have to replace a gearbox, they have to bring a crane out?
Yeah, you have to bring a crane out.
Yikes.
Yeah, so it's not, so you really don't want to replace those kind of things. And often when you do maintenance, as you wait until many things break, then you go and do maintenance. Doing it for one turbine, sometimes doesn't make sense. Okay, so these turbines are good, right, if they operate, but doing maintenance, like there's a lot of research on how to do maintenance better. Like this is really a pain for people who have to work on this kind of machines. And so maintenance is difficult, and also basically you have to turn the blade towards wind. So of course we want to do this, but that's just another difficulty, right, we have in building this. And another thing that's not to be discounted is local opposition. It's very hard to build turbines. There's actually nobody likes turbines to be very close to them. So question to you guys, has any of you been close to a big wind turbine? You've been close to a big wind turbine? Anybody heard how much noise do they make? Do you guys have an idea how much noise this makes?
No idea.
Yeah, so this actually, they're very, very loud. They are very, very loud in general. So this is like a big airplane lifting off. Like living close to this thing is like living close to the airport. Okay, these are not quiet machines.
Does the sound come from the blades to the air or through the internals of like the gearbox?
Oh, just blade through the air. It's like a jet. It's like a jet engine, basically. You have this blade spinning, right? So it's actually loud. It's fairly loud, this kind of thing. So if they ever, let us go outside again, every year we organize a field trip to the BPA wind turbines. So whenever we get the chance to do that again, I encourage, everybody to go and stand underneath it and see. You really get a sense of how large these things are and, kind of noise they can make. Right? So these are sometimes not the quietest machines we have out there. So that's why they generate a lot of power, but it's not always easy to build them. So you do see this type of designs somewhat increasingly. You see, there's designs that's called vertical axis turbines. Basically, as you just turn around and you have this sort of vertical blade spinning this way. So then the blade, this kind of blade structure is on top. And basically you have a gearbox and a generator at the bottom, at the base. Okay, so this is the gearbox and the generator. Okay. So you put this in the at the base of the tower, right? And everything above is the spinning blades, is the thing that captures wind power. So you do see this sometimes, right? They're getting somewhat more popular. Okay. And the advantage of this kind of vertical axis design, there is no need, right? So a yaw mechanism is basically something that turns a blade. But of course, this kind of design is, it doesn't matter which direction wind blows at. Okay? So you don't need to turn it towards the wind. And then the generator, so everything, gearbox, everything is at the base of the tower, okay? Right, compared to before, where they're at the top of the, or at the hub, right? These things are at the base, right? So this makes maintenance so much easier. Okay, so the maintenance is much easier for this. Right? So that's why you tend to see some of this vertical axis ones, especially in more urban areas, right? Whereas they're just easier to install, easier to get to, not as large as the horizontal ones. Okay. But again, the main disadvantage of this vertical ones is basically the wind speed is slower. Since you're right above ground, you have smaller wind speed. So you cannot get something like, let's say, a megawatt easily out of this vertical turbines. Then, because then it's actually, sometimes it's hard. So because the speed is low and the blades can still be heavy, it's actually sometimes hard to get this thing to start spinning around and generating power. Okay, so they're still not as popular, right? These kind of vertical ones are used much less commonly than the horizontal ones, but we're start to see sort of more of these pop up. Okay, so for example, if you ever design a microgrid, nowadays people are considering this sort of vertical axis turbines instead of horizontal ones, just because construction is easier and maintenance is much easier. Okay. You don't need to build something that's 100 meters tall and weighs a couple of tons, right? So you can build this fairly easier if you need a smaller amount of power out of it. So they're entering how we especially in microgrid considerations. Right, so we are not going to look at the vertical ones all that much. Okay, we're not going to look at the vertical ones. We're going to focus mostly on the horizontal ones. Although a lot of things we say about the machine applies to both. Okay, because now from now on, we'll basically look into this part of the structure. Right? We'll look into this part of the structure. So a lot of things we say about machines applies equally to horizontal ones and vertical ones. Right, and to emphasize again, a main thing that makes wind turbine difficult to maintain, and where a lot of innovation happening, it has to do with gearbox. So they contribute to a significant amount of weight. So a significant fraction of the housing of the that comes from in fact that we have gearboxes. So they fails. This is actually a common source of failure. That's quite common. These are the things that fails. And they also require regular maintenance. Because you need to do things like oil changes. Okay, so these are, you have to maintain them fairly regularly, but maintaining each one of them is just really hard. Okay, this is really difficult. So that's why we have new turbines. There's no gearbox. We really want not to use gearboxes in these new turbines. So nowadays, if you build a big turbine, most of the time you don't have a gearbox in between. Okay. So what do we do if there's no gearbox? Right. So gearbox exists, right, for good reasons. The speed conversion, basically. If there's no gearbox, what do we do? You still have a variable speed, right? The turbine, the blade still spins at variable speed. And then you want to get rid of this gearbox. Okay. Here's the gearbox. So how do we get rid of this gearbox?
Maybe you could generate DC and then use an inverter to connect it to the grid?
Right, so the idea is right, so what is gearbox? Is gearbox basically synchronizes the rotation of the generator to the grid, right? So gearbox is a mechanical way of doing it, right? That's a mechanical converter, right? We can do this also electrically. We don't need to convert things mechanically, right? So now there's a new turbine is this idea. You have AC, DC. This AC is variable rate. Okay, this is whatever the blade gives you. Okay, the blade spins at whatever rotation speed you want to spin at. That's fine. You do a DC AC again, this is 60 Hertz, right? So this is the gearboxless delay. And instead of doing a mechanical frequency conversion, we'll do electric frequency conversion. Okay? And if you have big converters, you can make sure the output is right. So if you have this kind of back-to-back converters, you can make sure the output is 60 Hertz. So that's the idea we have. Okay? So this is the new type of machines. We'll get there eventually. Right? So our goal is to go through the different type of machines. The last one we capture being this one with no gearbox at all. Okay? But we'll start from the simple ones to get to here. And this one is being popular because nowadays finally the power electronics caught up with the gearboxes. It's cheaper, it's more reliable. It's definitely a lighter weight than gearboxes, so that's why this is winning. Okay? And this is the trend we're seeing out there, right? So that's something to keep in mind, right? Why are there so many types of machines? Right? The idea is always, more controllability and get rid of this sort of mechanical components. You want to replace mechanical components with a kind of solid state. power electronics, right, which is more flexible for us and easier to use. Okay, so we'll get here. And one example of this kind of, right, so before we get to different types, again, we want to develop an idea of how big these things are. Right, so we look at this picture. This has 2 scale, so this is a minivan right here. Okay, so somebody took a picture, that's a car. So that's a car with somebody standing underneath it. I believe Professor Muhammad Ashrakawi took this picture, I think. So there's some graduate students standing there and somebody took a picture with a tower, right? So that's the scale of what these things are. Okay, so that's a car with people there. Right, so this tower is 80 meters, the blade length is 37 meters, right? So these are, give you a sense of how big these machines are. Okay? These are not small machines. Right? So again, this puts into more to a perspective as this will sweep out a circle with a diameter that's bigger than a Boeing 747. Okay, so these are, again, you can fit a Boeing 747 inside the area this thing sweeps out. And 40-meter long blades are not actually all that long anymore. You have bigger blades. Okay, so again, that's, these are big machines, weighs, is very heavy, right? Generates a lot of power, but the mechanical construction, the construction of these is not simple. Okay, so this is again a real picture. So for people who have questions how you build this, let's say this is part of the construction site. As you have these cranes, you need to build a big crane to lift all these blades. And when you construct one farm, it's like building many big buildings. You basically keep building you build buildings that's 100 meters tall, and you build lots of them this way. Okay? That's why you keep building them. Okay, and again, the rotor diameter is getting larger and larger. So, we started with 50-meter diameter. Nowadays, we're close to 200 meters diameter. So these are large machines, not easy to construct, not easy to build. Okay, so, so that's putting again the Statue of Liberty here, and again now the big turbines you see nowadays is bigger than the Statue of Liberty. It's definitely much taller than this. So one question is, remember, so this is blade length, right? So right now the blade length, we have about, the largest we have is about 100 meters. This is the largest we have nowadays. We got a bio one, this is the largest. Right, so that's about blade length is 100 meters. Okay. Can we build things bigger? Actually, constraint Y is 100 meters. Right? So from the wind speed point of view, the bigger the blade, the better. Right? You get, you're taller, right? The tip of the blade is taller, so you capture more speed. The bigger the blade, you sweep out a bigger area. Right? So ideally, you want as big a blade, as long a blade as possible you can construct. Right? So what's limiting us to 100 meters? We can build 200-meter buildings, right? It's not, we do that all the time. So what prevents us from building very long blades? There's actually a simple logistic reason for this.
They snap.
Not really. You can just we're fairly good at getting this. It's like building airplane wing. Yeah, transportation, like the chassis. You can't get it to where the wind turbine you want to put it. That's you run into transportation constraints. You run into transportation constraints. Basically, this is your trailer size limited. Okay, you cannot put an arbitrarily large truck on the highway. So the biggest trailer we have can transport about blade that's 100 meters long. We haven't gotten to a situation where we can assemble the blades yet, right? We cannot, assemble them on site. That's not something we're able to do. So you have to transfer the entire blade together, the one whole blade to your site. And a lot of times you can't get a truck that big to go where you want to go. Okay? So this is very hard. The construction is hard. And that's why, at least onshore, it seems we're running into a size limit. And the size limit seems hard to change with the current technology because you can't get the blade there. So that's the idea. So again, show a picture, right? This is a truck carrying a blade, right? It's hard to get a larger truck there. Okay? Hard to get a larger truck there. So that's the reason why what limits the size. So you look at offshore, you can build bigger. Okay? Offshore is relatively easier to construct larger machines, construct larger turbines with longer blades because you're not limited by the highway transportation system. But onshore looks like we're limited in size. So a lot of new innovation people are trying to come up with is in the sort of power electronics design, making things more efficient, and not necessarily just build bigger machines. Okay, so for the last several decades, there's built bigger things. Now this is swinging back to making things more efficient, rather than just keep constructing bigger. Right. Any questions about this? Okay, so this is sort of the physical infrastructure design for the turbines. So if you're interested, there are actually courses you can take, where if you're interested in building this actual turbines. So again, this is going into more detail is outside scope of this class, right? We're going to look at the electric machines more. But when you work with wind turbines, definitely think about this sort of logistic challenges. Right. So now let's look at controlling this turbines, which will lead us to think about different machines we want to use. This will lead us to think about different machines we want to use. So basically, as we covered before, is you want to maximize the CP, coefficient performance, right, through pitch control. Okay, through pitch control. Basically, you want to pitch your blade to optimize the tip speed ratio, then to optimize the coefficient performance you get from this. And all blades, most blades has this. So most turbines have this feature. You'll definitely need this so-called yaw control because you want to align the rotor to face wind. You want to align. And if the wind speed is too high, you want to lock the blades. Right? Basically, if the wind speed is too high, you actually don't want the blades to turn to generate any power. Right? So if the wind speed is too high, dumping power is difficult. So you lock the blade. Okay. So that's the control mechanism we have. And again, if you look at the speed power characteristics, even though so this is the theoretical, this is the wind power. So this blue line, wind power, is the amount of kinetic power in wind. Okay, so this is in theory how much power we have. Right, so in theory, the higher the speed, definitely wind contains more power. But if you build a turbine, again, we can only extract power in a limited range. Okay, so we need some cutting speed. We have some cut out speed, right? The operation range is, or you want to operate at this range. Okay? You want to operate this range, right? So again, higher speed is not necessarily better. Higher speed is not better. So this is just a measured curve. So this is a true measured curve of what the wind turbine performance is. Okay, so give an idea of, this is quite modern. That's quite modern turbine, and can generate sort of peak power over a fairly wide range of speed. This can generate peak power, quite wide range of speed. Okay, so that's the characteristic we want to have. Although getting here is not simple. Okay, so it's not always trivial to get here, right? So to get there, let's think now about generators. Okay, let's think about generator. Right? So if you remember 351, we basically have two types of generators or motors or machines. The first is induction. Induction machines. So these are asynchronous machines. Right? So induction machines generate or consume power because there's a non-zero slip. Right? So that's why they're called asynchronous. And then we have synchronous generators. Synchronous machines. So one question is there a difference between generator and motors? Right, so we think motors are loads, generators are things generating power. Is there a difference actually between them? Right, is there a difference between an induction generator and an induction motor? Right, so there is no difference. Okay, so that's why they're called machines. Okay, an induction generator is an induction motor with a negative slip. Okay, that's how it is. So the actual machine itself is symmetric. There's nothing distinguishing motor from a generator except the slip is operating. Right? So all these are symmetric things. So a synchronous motor is a synchronous machine, right? So it's generator, or you can think of a synchronous generator, a synchronous motor run backwards. Okay, so all these are exactly the same things. Okay, so that's why a lot of things we cover in 351 about induction motors applies directly here. Okay, it applies verbatim to generators because nothing changes in the circuit. Okay, there's nothing changes in the circuit except you flip a sign to change the power, change the machine from consuming power to generating power. Okay, but otherwise there's no difference. Okay, that's one thing to remember. That's why these are always sometimes called machines, right? So okay, so one thing to think about generators, synchronous generators, is let's look at induction machines. Okay, so this is induction generator. So this is induction generator. Okay, so this is IG as induction generators. And there we want to look at the fixed or variable speed. The reason we talk about fixed or variable speed is because when you think about induction generators, for folks who still remember 351, right? So we have an induction machine, just generator or load. This operates because by varying, right, by changing slip. Right, so you remember the slip is basically a normalized measure of the speed of the machine and the synchronous speed. Okay. So when you talk about slip, normally how wide is the range? Right? What are the operating range for a slip? Is it very wide or very narrow for induction machine? Right? So if you think about motor, how far away can slip get from zero? right? So we'll look at this later in this class as well, but normally slip is over normally the slip is changes over a fairly narrow range. Okay, so you cannot be too different from the synchronous speed if you look at a motor or a induction generator. And the issue that causes, if your operating speed, right, if your slip, if you can only operate at a very narrow range of a slip, you're basically what's called a fixed speed wind turbine, because your speed cannot deviate too much from the synchronous speed you have. Right? We cannot deviate too much from the synchronous speed. So what we end up is we have a very narrow. We end up with this quite a narrow operating range because you want to keep the slip in a very narrow range. So actually the wind speed cannot be too high, the wind speed cannot be too low. And you only generate useful power for this narrow range of speed, for this very narrow range of speed. So that's called a fixed speed wind turbine. It's the easiest one to construct, but sort of the least efficient one, right? The least efficient one in practice. And then one innovation in wind turbine design is to make a variable speed wind turbine. Basically, where it makes the operating range quite a bit wider. We can operate over a much wider operating range, right? So that makes the turbine much more efficient. Okay, you can capture power over a much wider range of wind speed. So that's one innovation we have, a sort of very important innovation, right? And nowadays, again, all the turbines we have are mostly variable speed ones, just because you can capture so much more power, right? Especially remember wind is probabilistic. Okay, so it's virtually impossible to guarantee wind speed as within this narrow band. Okay, so the wider your operating characteristic, your operating curve is, the more power you generate, right? So again, we'll cover different generators going from fixed speed ones because they're simple to understand and they form the basis of other ones. But the goal is to move to variable speed ones, right? To build turbines that can be useful over the widest possible operating range. So that's the idea. All right, so let's take a break now. We'll come back at 1:30. Okay, let's get started again. So if you look at the fixed speed and variable speed turbines, making a fixed speed turbine is really easy, actually. A fixed speed turbine is basically an induction machine. It's an induction machine. It's an induction motor run backwards, basically. Right? So these are just very cheap, very cheap, very robust. Where the main drawback is you have to operate within 1 or 2% of the rated speed. Okay, so that's our drawback of the generators. Right? So for loads, this is not a big problem because if you're load, you can count out the frequency from the grid to be 60 hertz. Right? So that is synchronous speed you can count out. So you can design everything with reference to that 60 hertz. However, if you're a generator and if you are a wind turbine, it's very hard to say that your rotation speed is always within 2% of the synchronous speed. So we have fixed speed, right? So we cover this. So variable speed, again, you operate over a much bigger range. The drawback is just as harder to, it's more expensive to build. Right? It's more expensive to build. Okay. So let's look at the different types of turbines, okay? Different types. And these types are actually, the names are in industry, sometimes they are only referred to by the type name. Okay, so people will say this is a type 3 turbine. Okay, so it's important to understand what each type refers to, because often they'll just give you the type. Okay, this is a shorthand used very often. Okay, so basically, type 1 is the earliest wind turbine we have. That's a fixed speed design. Okay, so this is just an induction motor run backwards. Okay, you have induction motor, attach blades to it, run it backwards, connect to the grid. That's the turbine we have. So when you look at variable speed ones, basically there's several types within variable speed. So type 2 is an improvement over type 1. Okay, so it's basically, we'll cover what each of these means. It's a little bit more, you have a little bit finer control, right? It gives you a wider operating range. Type 3 is quite commonly used in practice. This is called doubly fed induction generator, or you see this as DFIG. This is quite common. There's a lot of existing turbines. That's type 3 or DFIG. What this is used as is basically you have another path. Okay, so in addition to an induction motor, there is also a power electronics. There's sort of a power electronics path between the farm collection point and the generator. Okay, so so it's doubly fed because there's two paths for current to flow. And then the new one is called synchronous generator. And this is basically replacing an induction machine with a synchronous machine. Okay, and you get rid of the need to have a synchronous speed. Okay, we don't need a synchronous speed anymore. And this is sort of a full solid state design, converter design. So these are different types. We'll get to all of them. This will be a big focus for us in the next month. Okay, so if you look at where the class is going, probably midterm will happen around this point. Okay, so midterm, we'll probably have the midterm after we do type 3 turbines. Okay, so that'll be where the midterm is. Then we'll do type 4. They'll go on through with the rest of the class. Okay, so but the next month, we'll go through each of these machines, okay, each type of machines. So given these types, right? So before we get into the types, one housekeeping thing is to understand sort of what goes on around the machines. So if you look at a turbine, so we're going to draw this, right? So the turbine has to connect to the grid, right? So we're going to draw this from the grid from left to right. Okay, so the way the farm works is there is a grid connection point. Okay, so this is where we interface with the grid, right? So this side is a grid. So what this collection point is basically is a big transformer. Okay, so you can think of this as a voltage transformer that transforms voltage to the grid voltage that we need. So there's a line called the trunk line. This is a line inside the wind farm. This is a line inside the wind farm. And then we have another transformer, basically. And what this transformer does is transform the voltage to the trunk line voltage right after the generator, right after the wind generator. Okay, so this point is called the farm collection point. Right, because this is where each generator, so let's say this is a generator. So if we have a gearbox, this is a gearbox, and this is the blades. So the generator collects the farm collection points, goes to a transformer. go through a trunk line, then connect to the grid side transformer. Okay, so this is what it looks like. And normally we'll have some capacitor here. So normally we'll have a fixed compensation, fixed capacitor for voltage. Normally you have this capacitor here, right? And this is a, okay. Right. So we do it this way because, right, so this is a farm connection. So normally often when we draw, is we'll only draw this part. Looking at a turbine. Okay, so we should keep in mind that there's several transformers to get to the grid. But when we draw it, we often draw to the farm collection point, right? And drawing to a farm collection point basically means that this is where turbines from one farm are tied together. Then they go to the grid. But since everything after the farm collection point is the same, there's no difference. So we often just draw it up to the farm collection point. So for example, right, so if we draw a type 1 induction generator with fixed compensation, the way we'll draw it is there's a farm collection point, there is a capacitor, there is a induction generator, a gearbox. Right? So that's the way we'll draw it. Right? So we just assume that. Okay, we'll just assume that the rest, after goes into the farm, there is a way to get to the grid. This is our idea. So this is fixed compensation. Right? So of course, the first, the sort of the simplest thing, right? The simplest modification we can make here is make this a variable capacitor. Okay, so the first thing people did after this, building this type of induction generator, type 1, is make this a variable capacitor. Okay, so instead of fixed capacitor, you make a variable capacitor. So it's at least we can handle voltage issues a little bit easier. So that's one thing we can do. But even with a variable compensation, right? Even with variable compensation, your operating range can still be a bit narrow. Can still be a bit narrow. So type 2, okay, type 2 is an improvement basically over type 1 that gives us a little bit wider operating range. So it's still an induction generator. This doesn't change. There's a gearbox. This goes through the blades. This goes through blades. So is there a way you can think of that can improve the operating range? What can we put around this induction generator to make the operating range a little bit wider, to give it more control? Okay, so one way we can do it is this way. As we collect, basically you put a diode, a sort of switch. Okay, we'll put a switch here. And we attach a variable resistor in parallel to the generator. Okay, we add a variable resistor here. So what this variable resistor does is basically it allows us to burn off additional power. Okay, so sometimes if the wind is blowing, for example, at too high of a speed, and you want to slow down the turbine, right? You want to slow down the speed a little bit. You want to control the speed. One way to do it is basically just burn the power through a load. And this type 2 attaches a variable resistor to the generator, okay, to get rid of this load, basically. Okay, so if there's, if one blows at too high a speed, this is the way to dump power. Okay, we can dump power this way. Any questions about this? At least in a conceptual idea? Okay, so what you'll see is in machine design, turbine design, often the trick is to get rid of power. Okay, so it's not generating power, it's how do you get rid of this excess power? How do you dump this power in a short amount of time? So this one idea, this to dump power, is to just add a resistor in parallel with a switch. Okay, you dump power when you close the switch, right? So this is a really simple idea. Right, so this is obviously not very efficient. Okay, this is obviously inefficient. If your control mechanism is just burning power, right, as heat. So you can improve this a little bit, right? Actually, you can improve this by getting rid of power in another way. And this is the DFIG, type 3 W-fed induction generator. Okay, so what this design says is, I still have a generator, a gearbox, things like this. Gearbox, blade here. But hey, let's say I want to get rid of power, right? Let's create another path for power to go through. Okay, let's create this path for power to go through. Let's add to converters. Okay, let's add to converters. So this is called doubly fed because now there's two paths for current to flow. Current can go, in both directions, let's say. Current can go in both directions. And what this happen allows us to do is this is a sort of flexible current flow. This can provide reactive power. Okay, so one thing about induction generators, they can only consume reactive power, whereas this two-path system allows us to provide reactive power. Okay, so this is a quite advanced idea with reactive power, right? And the trick here is in this sort of DFIG design, the power electronic path carries lower power, carries sort of a smaller fraction of power compared to the main path. Okay, so in this type of design, this is not a fully gearbox-less design because what happens is the power rating is about 1/3 of the generator rating. Okay. You can think of 2/3 of the power or current still go through the sort of the main path to the farm collection point, whereas 1/3 is sort of flexibly controlled through the converter path, through the path with converters. So this definitely gives us a much wider operating range, a much wider operating range, but it's not full, it's not full converters because they don't carry most of the power. They still carry sort of relatively small amount of power. Any questions about this setup?
I guess a quick question. The box that you've drawn, what does that represent?
Gearbox. It's
Okay.
related to draw gearbox.
Okay, thank you.
Yeah. Yeah. So we still need a gearbox. Yeah, we still need a gearbox. Right. So, but again, another nice thing about this sort of design with converters in the past is we can do control much easier. Okay, the control can be done much easier because of this we covered before. So the way we do control with this converters is following now. So again, these are the induction generators. This is the gearbox. blade. The way we do control is as we add a feedback loop into this box. Okay, so this is a measurement. This can control things like, this can measure pitch angle. And sorry, let me draw this better. Okay, so we have a box called the AGC box. So this is automatic generation control. What this does is this takes information, for example, as pitch angle, things like wind conditions, and then you can synthesize a voltage. Okay, you can synthesize a voltage signal into your converter box. And the good thing about this is this controller, this AGC controller, now is a digital control. Okay, this is now a digital control system, right? Because what we're doing is we're controlling the AC/DC converter. Okay, so we're now able to do digital control. Whereas if you look at things like type 2, right, still sort of this mechanical feedback control. And anytime you can do digital control, that makes life much easier. You can implement control laws very simply, right? You can write them in software. Okay? You can, put many measurements together, come up with whatever control laws we want, and we can implement them very easily. And so this is actually quite useful in practice, okay? Because you can rewrite the control mechanism using firmware, right? You no longer, we don't need to do any sort of hardware updates to this. We can write control laws in firmware, and that makes things much easier to do, right? Compared to sort of a mechanical feedback design. Okay, so this type 3 allows us to do full digital feedback. Okay, so this is very useful, quite useful to have in practice. Then, if you look at the type 4, so type 4 is as the AC to DC converters gets better and better, what we can do is we can get rid of the gearbox. Just have this kind of converter. So this is now a synchronous generator, but we don't need a gearbox. So of course, we need to do excitation for this generator. So you have exciter, you tie it to the synchronous generator. Right, so this is quite, again, fairly easy. It's an easy thing to do if we can build good converters. Right, and this again allows us to do full AGC for automatic control. Right, so we have this sort of AC/DC, synchronous generator, blades. We have an AGC box, our digital control box. Again, let's say we measure pitch angle, and we can create control signals. Okay, we can very easily create control signals. Okay, so type 4 is the most turbines that's being constructed today will be type 4. We're getting very good at building this type turbines. Right, and then type 3 is definitely used in practice as well. Okay, so we do see type 3 quite a bit in practice because a lot of the ones constructed, let's say, over the last decade will be type 3. Okay, but nowadays, new ones will be type 4. Okay, so here we'll stop here today. Next class, we'll start with type 1. We'll sort of build up to type 3 and then to type 4. Right, for the next class, the type 1 is really reviewing how induction motors work. Okay, so our next class will be to review induction motors work, how they work, right? Remind us what is the slip, what is things like developed power, what's the air gap power, what are all the things. Then we'll build around that equivalent circuit model to adding things like variable resistance, to adding things like this sort of AC, DC, DC, AC converter link, to think about this type of, think about them in one sort of equivalent circuit. So we'll start that next class. So the homework for this week should be posted later today. Any questions? If not, I'll see you next Tuesday.
I have a question about the type 3 generators, how they're, are there two kind of separate stators on the induction generator? And that's what, like how the AC, DC, DC, AC is connected separately?
No, still one stator, still one machine. Still one machine. Yeah, so we'll see that this basically goes into the slip part of the induction generator. So we'll see that we'll get to type 3. Yeah, we'll see how this works.
Okay.
So more detail on this, basically the ACDs, the converters look like a load, a developed load on this. Basically as a developed load to this, and that in turn impacts the slip. Other questions? All right, okay, thanks guys. See you next week.
Thank you.
Thank you.
Thank you.